All right, so welcome to Math 140, Calc 2, Lecture 25. And what I want to be doing today is I want to start talking about differential equations. So out of curiosity, how many of you have taken a physics class? How many of you have taken a physics class before taking calculus? Okay, so I have strong views on many subjects in the board, as you will find. I am not a huge fan of doing physics before calculus. I think the more math you know, the easier it is to do physics. It's always an interesting question as to what order should you be doing the material in different classes. So what I want to do today is I want to talk a little bit about an introduction to differential equations. I want to talk about Newton's laws of motion. I want to talk about ways of solving differential equations. Trying to reboot to see if it will try. Sometimes it's going up and on. All right, so hopefully this will post up in a second. All right, so how many people are familiar with Newton's laws of motion? So what are the Newton's laws of motion? Objects in motion tend to stay in motion. Good. What else? It's 3. Every action has an equal and opposite reaction. The last. Nope, that's thermodynamics, which Woody Allen has rephrased as sooner or later everything turns to shit. As time passes, things go to maximum disorder. So what's the equation we associate with Newton's laws of motion? F equals ma. So force equals mass times acceleration. The worst I've ever seen this written was P equals mf in a physics textbook, where P was force, m was mass, and F was acceleration. You can use notation like this, but you're going to confuse everybody. You know, P we normally think of as momentum, F is maybe a frequency. We normally use F equals ma. This is one of the, if you had to choose like 2 equations of physics, this would be one of the 2 that people should know. Anybody know the other one? E equals mc squared. And so I think when Stephen Hawking was writing his book, A Brief History of Time, I think somebody told him every equation you use results in half of your audience being lost. So that's fine. I'm willing to lose it for this. Yeah, these ones are extremely important. So we're going to apply this in a setting near the Earth's surface. So in the Earth, near the Earth's surface, we have gravity going down. We normally denote it by G. Anybody know the units of G? Meters, not meters per second. Meters per second is a speed. Meters per second squared. Yep, it's a acceleration. And so acceleration is the change in velocity over time. And so if x of t is distance, then dx dt equals v of t is velocity. And the derivative of velocity with respect to time is the acceleration. So here I'm doing a one-dimensional motion. You could, of course, do 2-dimensional motion. You could do 3-dimensional motion. It gets, more and more involved. We're going to assume that the gravity is pretty much constant near the surface of the Earth. Does anybody know approximately what G is? Approximately 9.8 meters per second squared. If you know what it is approximately in feet per second squared, forget that. We don't do things in the English system. I think it's around 32, but it's been so long ago. So I'm not going to draw things to scale. Here's the Earth. Here's the center. Here's the radius of the Earth. Anybody know roughly how big the radius of the Earth is? 100 miles, 1,000 miles, 10,000 miles, 100,000 miles, within an order of time. I knew it in miles, and I just quickly converted it to miles. It's about 4,000 miles. So I quickly looked up, it's about 6,400 kilometers. So let's estimate it as, approximately 6,000 kilometers. It's a nice round number. Newton's real law of gravity is the force between two objects is equal to the product of their masses divided by the distance between them squared. So if I have a mass, near the surface of the Earth that's being pulled down, and let's call the Earth maybe M1 and this M2, then force is equal to G M1 times M2 over R squared. So GM1 is a constant. I'm sorry, I wrote M2, it should be M sub 2. And if we're supposed to have this as equal to the mass times the acceleration, that gives us the acceleration should be GM1 over R squared. Let's try to think, how much is the acceleration going to change as we move the mass a little bit? So we have the acceleration due to the Earth's gravity is a function of R. So what would be the acceleration as a function of R? So it's on the board. What would the acceleration be as a function of R? G M1 over R squared. And do you know its value at any choice of R? G is a constant. So I tell you that the Earth radius is about 6,400 kilometers. And what did you tell me little g equals at the Earth's surface? 9.8. So do you know the value of the acceleration at any value of little r? So near the Earth's surface, yeah, so what radius would that be? Yeah, 6,400. If we use r for the radius of the Earth, at this value of r, it should be approximately 9.8 meters per second squared. Right? And now we could ask, what would happen if we increase by a little bit? Well, unfortunately, there's two unknowns. We know the radius of the Earth, but we don't know G or M1 without resorting to some serious science. And for years, it was a huge question. What is the value of Newton's gravitational constant? You might have seen Cavendish's experiment where he has two masses hanging from a string and then two other masses, and you're looking at the torque and how much things are twisting. It was a very challenging problem to determine exactly what is G. But if we only care about the product, GM1, that we can do. And so we know at the surface of the Earth, this product is about 9.8. So now if we wanted to estimate A of R plus 1, how would you estimate that? Well, the first thing is to just say it's still 9.8. But we know a lot about calculus. How do you estimate a function? Maybe there's a reason that this unit is following the unit we just did. Maybe I'm not just making things up on the spot. Do a Taylor series. So it should be about what point? Not -1. Where do we want? When you Taylor expand, you want to expand about a point where you know things. What point do we know things at? R. So Taylor expand about R equals R. We would get, it would be A of R plus A prime of R times R plus 1 minus R. That would be the first order Taylor series. No, we're Taylor expanding about the point R. We know what's going on at the point R. We have to do our Taylor series expansions about 0, but it's whatever point is of interest. The point of interest is not 0. The point of interest is equal to big R. That's where we know what the value is. We know what A of R is. So A of R is 9.8. What is A prime of R? A of R is GM1 over R squared. Well, I like to write this as GM1 R to the negative 2. So what would A prime of R be? Is to GM1 over R cubed. So this would be minus 2 GM1 squared times 1. Why did I write R cubed as R squared times R? That's a strange way to write R cubed. So much of life is doing it. Because that's A of what? That's A of big R. We know what that is. And actually, I'm sorry, this should be evaluated at capital R. Because we're substituting in your A prime of R. So this is just 9.8 minus 2 times 9.8 over 6400. So if we do 9.8 times 2 divided by 6400, and we subtract that from 9.8, we get that this is approximately 9.7969. So if we go up an entire kilometer, we're going from 9.8 to 9.7969. It's not changing a tremendous amount. And that's going up an entire kilometer. If we went up much less than a kilometer, the change would be very different. For a plane, do you think this would actually matter? If a plane is going up 5-6 miles, that might be enough, sort of, it's not to matter. Definitely by the time you get to satellites in low Earth orbit, it's going to matter. But in the classroom, if we go up a meter rather than a kilometer, you would replace this. Oh, wait a minute. Yeah, you would replace this by, instead of having a 1 over here, you would have a 1 over 1,000. And so the change would be very red. I mean, our change was less than 0.01. And so we're just going up, a meter. There's so little change. This is why we can assume that the acceleration is essentially constant near the Earth's surface. The Earth is not a sphere. I think I sent you the Asimov article about the relativity of wrong. I will email Asimov's article on the relativity of wrong. The Earth is not quite a sphere, but it's close. And for a lot of calculations, you can approximate the Earth as a sphere. Right, so now let's do some physics. So near the Earth, G is approximately equal to 9.8 meters per second squared. So what we can do is we can say we drop a ball initially at height h and ask you what happens as time passes. And so we have to decide how are we ordering our coordinate systems. For this, I would probably orient my coordinate system so that positive y is going up, negative y is going down. So this would be my y-axis. So what is my initial height at time 0? H. And then is my acceleration positive or negative? Is it pulling me up or pushing me down? Down. So I would say the acceleration as a function of time is negative 9.8. And what's the initial speed? 0. So I'm using y, not x. Why am I using y rather than x for distance? Why would I be using y for distance rather than x? Yeah, because I'm moving up, down, so I want to use y. Why don't I use d for distance? What's the velocity here? How is velocity related to distance? It's dy dt. Okay, it should hopefully be clear now why I don't want to use d for my distance. I don't want dd over dt. Terrible. Don't use d as a variable, don't use d as an variable. What is the initial speed if I'm releasing it at rest? 0. So I know I start at time 0 at height h, my initial speed is 0, the acceleration is always negative 9.8, v of t is the derivative of y with respect to t, and what's a of t? Negative 9.8, but in terms of the y's and the v's, what's a of t? It's dv dt, or it's d squared v dt squared. So this means two derivatives. So this is how we write two derivatives. We write d to the 2 over dt squared. We could also write this as v double prime of t. I'm sorry, this is not v, this is not v, it is y. So we have a second order differential equation to solve. We want to solve y double prime of t equals negative 9.8. We could try to solve it directly, or we could just do it in stages. So stage 1, we would have a of t equals v prime of t equals dv dt is negative 9.8. So can you give me all functions whose derivative is negative 9.8? No, close, it's not negative 9.8. Negative 9.8 t, we're using t as time, plus c. But there's a special value of t that we know. What value of t do we know things about? 0. But v of 0 equals 0, so c equals 0, so v of t is negative 9.8 t. Okay. Now that we know that, we know y prime of t is dy dt is equal to v of t is equal to negative 9.8 t. So what function has derivative negative 9.8 t? Negative 4.9 t squared plus c as y of 0 equals h, c equals h, so y of t is equal to negative 4.9 t squared plus h. Yep. And then you can even calculate such things as when will the object hit the ground? So because we know how to find antiderivatives, we can actually solve equations like this. Instead of dropping something from a height, what could we do instead? We could throw it. And so what if instead we start at height 0 and say throw something up? And so maybe now the initial displacement is 0. What do you want the initial speed to be? 10 meters per second, okay. And so now we would have acceleration is equal to negative 9.8. So we would solve dv dt equals negative 9.8. So v of t is negative 9.8 t plus c. V of 0 is equal to 10. So what is c? So c would be 10. So now dy dt equals v of t is negative 9.8 t plus 10. So y of t is negative 4.9 t squared plus 10t plus c. As y of 0 equals 0, what does c? Zero. And so now we have a complete solution. If instead of doing y of 0 equals 0, what if we instead had y of 0 equals h? If instead y of 0 equals h, then what would c equal? So y of t is negative 4.9 t squared plus 10t plus c. C was now h. And so if y of 0 equals h and v of 0 equals 10, then y as a function of time is negative 4.9 t squared plus 10t plus h. And so we have, the height is basically given by a parabola in terms of t. So what question might you ask? What's a natural question that you might want to ask? So when would the ball hit the ground? Right, so how much time until it comes and hits 0? What else might we want to ask? What's the maximum height? Could also ask, at what point in time does it hit the maximum height? What's the maximum velocity? So what do you think the maximum velocity would be? So if we start at the ground, its maximum velocity is going to be when you release it and when it returns to the ground by symmetry. But if you release it at height h, when's its maximum velocity going to be? Right before it hits the ground, which would be greater than 10. So how would you figure out where it has the maximum height? Just a second. For people in Zoom land, I'm getting some stuff from your computer. Could you put on mute if you're not talking? Thank you. Are you trying to say something? Okay. So how would we find where we have the maximum height? We could graph, but what else could we do? How else could we find other than graph? We could find where the velocity is 0. So maximum height is when velocity is 0. Or and y of t is maximized. So we said v of t is negative 9.8 t. So v of t is negative 9.8 t plus 10. So v of t equals 0 means negative 9.8 t equals 10. So t equals 10. Sorry. So we have 9.8 t equals 10. So t equals 10 over 9.8. Knew that this was coming by choosing initial speed to be 10, not 9.8, but that's fine. So this gives us the value of t where it's going to be largest. Or we could use y of t is negative 4.9 t squared plus 9, I'm sorry, that was plus 10t. Plus 10t plus h. So how would you determine where y has its maximum? Well, but I'm saying, if I just look at this parabola, how do you determine where a parabola is maximized? I give you a function. How do you tell where a function has a maximum or minimum? The critical points at the end. It's not going to be the endpoints. So how do you get the critical points? You get y prime of t is negative 9.8 t plus 10. Oh, wait a minute. That's exactly what we had before. So if we try to just analyze the parabola directly, more generally, if I give you, say, f of x equals ax squared plus bx plus c, then the critical points come from f prime of x is 2ax plus b equals 0 at critical points. So x equals negative b over 2a is the vertex coordinate. So if I give you a parabola, it's just negative b over 2a. You can see this by putting the parabola into vertex form, by writing f of x as a x minus h squared plus k, and the vertex is hk. And you can just figure out what are h and k in terms of a, b, and c. You know, h is going to be negative b over 2a, and so on and so forth. Okay, so this is standard differential equations just moving up and down. The next most complicated thing is to imagine, we have a situation now where we shoot off a ball at some angle. And we'll assume we shoot it off from the ground. And then it's going to take some kind of trajectory. And then the key thing is going to be, what is that initial angle? And so we have gravity coming down, 9.8 meters per second squared. Does the gravity affect the vertical speed, the horizontal? Just the vertical, just pulling it down. So when we initially launch it, say we launch it with the speed of v. The initial speed is just going to be in the x direction is going to be what? Note 0, we launch with the speed v at an angle theta. So it's initially launched with a speed of v at an angle of theta. What's going to be the x component of the speed? So we would want the x component and the y component. What would the x component be? Breaking this hypotenuse up into two sides. So not cosine theta, v cosine theta. And the y would be v sine theta. And note, v cosine theta squared plus v sine theta squared square root is just v. So this splits our speed into a horizontal component and a vertical component. So the x component is just v cosine theta, and the y component is just v sine theta. So if I want to figure out how far it travels, well, nothing is changing the x component. So can you tell me what is the acceleration in the x direction as a function of t? What would that be? Zero. And a little bit of, you can get that at any point in time, its location is just going to be v cosine theta times t, because the speed is constant. You can go through, you can solve all the differential equations with the initial conditions. Oh, I'm sorry. This is not x of 0, y of 0. These are the speeds. So I should be using the letter v for speeds. So we'll call this v sub x and v sub y for the speed in the x direction and the speed in the y direction. So because speed is constant, the x distance is just going to be my initial speed times the elapsed time. The y direction is harder. So what's the acceleration in the y direction? What is that equal? Negative 9.8. So we get d vy dt is going to be vy prime of t is going to be negative 9.8. So what is vy of t going to be? Negative 9.8 t plus. Let's see if we can do this a little bit faster. We know what v of 0 is. What is v of 0? What's the initial y speed? V sine theta. I can just put a v sine theta here. This is just okay, so we know this. Now let's find dy dt, which is y prime of t. And so what would that be? So that's supposed to be vy of t, which is negative 9.8 t plus v sine theta. So we get y of t is negative 4.9 t squared plus v sine theta times t. And what's the initial height? At time 0, what's the initial height? 0. So now we know a function of y. We know our function of x. So what are questions we could ask? So what questions could we ask? Maximum height. What else could we ask? Time it takes the ball to hit the ground. How far the ball goes to the right. Now this was done at an angle theta. What might you want to know? I'm sorry? Well, we get to choose theta. So what might you want to choose theta to? What might be your objective? Yeah, what theta gives you the maximum distance? You know, let's imagine that you are an artillery commander and you are trying to shell an enemy position. And you want to figure out, well, what angle do I choose to shoot the cannonball as far as possible? The problem becomes a little bit harder if you're not at height 0 times. But you can change this. And so as an exercise, you can go through, and now what you can do is you can figure out what is the theta. For a given value of theta, what is the time that gives you the where the ball hits the ground? So what's the time of flight? So what must be true about y of t when it hits the ground? So y must be 0. So t max satisfies y of t max is 0 is negative 4.9 t squared plus v sine theta of t. Right? So t max equals 0 or v sine theta divided by 4.9. Because I can factor out a t max for both terms. So clearly, when t max equals 0, okay, well, that's actually just the starting point. And then we did negative 4.9 t plus v sine theta equals 0. So the time it takes is v sine theta over 4.9. Well, x of t was v cosine theta times t. So the maximum distance is at t max, which was v sine theta over 4.9. So maximum x distance is v cosine theta times sine theta over 4.9. So how do I find the angle that maximizes this? I could find the critical points, right? Is this a hard function to differentiate? So why am I putting a picture of Henry David Thoreau? Simplify. You've got cosine theta, sine theta. Does anybody recognize the function cosine theta, sine theta? What was 4.9? 4.9 was, how do we get 4.9? Where did 4.9 come from? 9.8 divided by 2. So let's restore it. So the maximum x distance is v cosine theta sine theta over g over 2, which is the same is 2v cosine theta sine theta over g, or v over g 2 sine theta cosine theta. Does that look more familiar if I write it like this? So you have 2 sine theta cosine theta. So this is just v over g times the sine of 2 theta. So if you remember your trig identities, the sine of x plus y is sine x cosine y plus cosine x sine y. The sine of 2 theta is 2 sine theta cosine theta. This is the advantage of understanding your identities, is if you understand your identities, you can quickly look at these things and see relationships. Where is sine of 2 theta maximized? So what value of theta is sine of 2 theta maximized? Now we're just talking about the sine function. Where's the sine largest? What angle corresponds to the largest value of sine? 90 degrees. So it's maximized at 90 degrees or pi halves radians. So where would sine of 2 theta be maximized? Yeah. So sine has a max at pi over 2. So sine of 2 theta has a max at pi over 4. of 45 degrees. So if you want to figure out if you start on the bottom and end on the bottom, what is the best angle to hit? It's 45 degrees. If you don't remember that, you would then have to study, say, g of theta is, I'll do it as 2b over g sine theta cosine theta. So g prime of theta, this allows us to review some rules of calculus. It's going to be 2b over g sine theta cosine theta, and we want the derivative. So what's the first rule we use to evaluate the derivative? First rule we would use. We use the point. Not the quotient. The constant rule. We have 2bg. 2b over g, that's just a constant. So the very first thing we do is we pull the 2b over g outside, and now we have sine theta cosine theta. Now what rule do we use? Now we use the product rule. And if you have a of x, b of x prime, that's a prime of x, b of x, plus a of x, b prime of x. So this would be 2b over g. What's the derivative of sine? Cosine. So we'd get cosine theta times cosine theta. And now we have plus sine of theta. And what's the derivative of cosine? Negative sine of theta. So this is equal to 2b over g cosine squared of theta minus sine squared of theta. So g prime of theta equals 0 means cosine squared theta equals sine squared theta. So when do the sine and the cosine are the same? At 45. So theta equals pi over 4, or what else? We could do 3 pi over 4, but without loss of generality, 0 less equal to theta less equal to pi halves. Because if I'm shooting the rocket with cannonball to the right, well, okay, that's if I want to shoot it to the left, I can just flip my lefts and my rights. So plus 0. So without loss of generality, I might as well assume plus 0 that my angle is between 0 and pi halves. But without loss of generality. So WLOG is without loss of generality. Whereas a friend of mine said freshman year in college, without loss of generosity. So the whole point about this is that we can, very easily solve a variety of problems. So how many of you have seen problems like this in your physics class? Right. Right. Well, do they give you, like Moses coming down from Mount Sinai, here are the kinematic laws of motion, and this is, if I give you constant acceleration, this is what velocity is, this is, without telling you where they come from. Yeah. Yes. Yes. I understand that this is being recorded. I am not a fan of this method of instruction. You don't need to learn that much calculus to actually prove these laws of kinematic motion. You just need to know what is the concept of the derivative and what are derivatives of simple polynomials. So we did some very simple differential equations today. We essentially said, assume the acceleration is constant. That's got to be the pretty close to the easiest kind of differential equation I can give you. Something that's, the rate of change of something is constant. Explore the consequences. So what we'll do tomorrow is we will explore what happens if you have more interesting kinds of behavior. What if the acceleration is not constant in time? Can you figure out what happens? And how do you take into account issues like that? There is a whole class on solving differential equations in just one variable, and then there's another class on solving differential equations in several variables. Not surprisingly, the more involved the equations are, the harder these are to solve. fortunately, many things in mathematics and the world that we care about are well modeled by differential equations of order at most 2, which is really nice because the more derivatives you have, the more complicated it is. The more cross terms you have, the more complicated it is. So the simpler things we have, the easier it is. Many things in life, however, are too complicated to be solved exactly. So I think the only atom we truly understand is hydrogen. With typically one proton and one electron in some kind of quantum orbital around it. When you get to something like uranium with over 200 protons and neutrons, the force of interaction is so complicated, we can't even write things down anymore in terms of just how bad the equations are. So what we'll do tomorrow is we'll talk a little bit more about some of the different types of equations that we can study. And then maybe on Friday, I'm not sure, and at some point I'm going to give a lecture on applications of differential equations to the Battle of Trafalgar. So the great Admiral Nelson had an intuitive understanding of how to apply the mathematics to optimally attack the combined Spanish-French fleet. All right, this is a good place to stop.